Welcome to the videos for the lab on beam deflection. In this lab, we'll just be loading a beam in the center so that we get this distribution of moment, and we'll be calculating what we theoretically believe the deflection should be, and we'll also be seeing how that compares to in practice what the deflection is, and we'll be calculating the Young's modulus for this beam as well. This first video is just sort of an overview of the lab. Have fun. The setup for the beam deflections lab for pure elastic bending will be exactly the same as it was for the moment strains and stresses lab. The eagle-eyed among you will probably notice it's the same video. So it's going to be exactly the same setup that you remember, where we're going to have a simply supported beam, and it's going to be loaded. I guess we could draw it like this, with a little relatively rigid bar, comparatively rigid, or a little thing right there to spread out this load right here. So that's just going to divide our load P into 2 points onto this. So we're going to have that. We're going to increment this with the jack, and that's going to mean that our shear diagrams, because of symmetry, our shear diagram will look like this, popping up to 1/2 P over to this point where 1/2 P is applied, down to 0, over to where the other half of P is applied. I overshot there, sorry about that. Down to here, over here, and then back up to 0 where the other 1/2 P is applied as a reaction. And then our moment is going to look very similar. I mean, not at all similar, I shouldn't say that. It's going to have a positive slope up until the end of this. It's going to be constant from here to here. And then it's going to have a negative slope from there to there, and we're going to end up at 0. So this is P over 2, and this is negative P over 2, and then this is going to be P over 2 times whatever this distance is. We'll call that A, and that also A. So then this becomes P A over 2. So that's our shear and bending moment diagrams. So what we're looking for in this one is not the stress and strain at some point right there and some point in there. What we're looking at is the deflection and the slope, or the rotation that we get in the beam. And we're also going to be looking at what the Young's modulus must be for all of these things. So there's going to be 4 steps to this analysis. The first is going to be you're going to talk about the deflection and the slope derivation. So you're going to use these theoretical values, right, for this theoretical shear and bending moment diagram, you're going to use the integration approach to determine what the theoretical deflection should be. Then you're going to use that and to determine the rotation over here, or over here, I guess, if you want to be wild. Please do it over here. And the deflection under here as a function of x. Then you're going to use those because you're going to leave E and I as well, please use everything basically as a variable. L, P, these distances A. You can leave all of those as variables and use things like this to get that written out. And then at the end of the day, you can pop in the values for the constants that we know, and you can use that to determine what the Young's modulus is, because that's obviously much more difficult to measure than the second moment of inertia. You can measure that by measuring the dimensions of the beam, the length A and length L. Well, yeah, again, you can just sort of whip out a tape measure or calipers if you're being more specific in this case, and P is also fairly easy to measure. So you'll use those theoretical values and equations you've determined to create the theoretical values for the Young's modulus, and then you'll compare those, and then you'll plot what you think the deflection ought to be based on theory against the actual values of the deflection, which will be provided to you there. Look like this. I'll probably make a new exam sheet that hasn't been copied. It isn't a copy of a copy of a copy for you to use, and you'll compare those the theoretical to the actual, and then you'll determine what the experimental value for the Young's modulus should be based on the theoretical deflection you have. Should give you what E is as a function of deflection, and then you should be able to compare and contrast those things. All right, we'll go into more detail in separate videos.